Okay, everybody, welcome to this last part to Chapter 4, our reactions in aqueous solutions. So this last section, what we're going to talk about here is, in our textbook, is Section 4.5. So you want to take a look at any details there. Section 4.5 is where you're going to find them. That is where we are discussing redox reactions. By the way, oftentimes reactions can be abbreviated with R and the X. I use it sometimes. Anyway, redox reactions is a short way to say an oxidation-reduction reaction. So that's what redox means: oxidation and reduction. So our definition for redox reaction is a relatively simple one. These are reactions that involve a transfer, there's an E there, transfer of electrons being our E negative. So any reaction that involves electrons being transferred from one thing to another would be classified as a redox reaction. Now, a redox reaction can be any type of reaction, right? It could be a single replacement, it could be a double replacement, it could be a combustion, it could be synthesis, it could be decomposition. Any of them could be further classified as a redox reaction as long as there is a transfer of electrons. As long as that happens, we call it a redox reaction. So keep that in mind. Now, this movement or transfer of the electrons occurs. Movement occurs from the reactant, or one of the reactants, with a less attraction of electrons to the product with a greater attraction. Makes sense. The reactant was holding on to its electrons, but then came in contact with another element or another chemical that has a greater pull, a greater attraction for those electrons, and so they get transferred. Is really a simple explanation for the process. Okay, next we're going to talk about some terminology, words that we want to be familiar with. So I'm going to go ahead and go to the next page. Okay, here we go. Let's define oxidation and reduction. What does oxidation mean? Again, simple definition: loss of electrons. And reduction, if you're a fan of opposites, means gain of electrons. Gotta love opposite definitions. If you know one, you technically know both. Now, there are some helpful ways to remember what these two words mean. I'll share with you what I feel is the most popular one. Let's go ahead and switch up. I'm going to switch up color. Here we go. Let's do this. OIL. Oh boy. RIG. It's a phrase, oil rig. Oil rig, relatively easy to remember, is a great way to remember that oxidation is losing. And maybe you can figure it out. Reduction is gaining. So oil rig, great phrase, very helpful in remembering which one's which, oxidation reduction. It can be very easy to get them mixed up. You definitely want to know which one is which. There are lots of other little devices, mnemonic devices, that you can find that help you remember them. I always thought this was actually the easiest and simplest. to know and remember. Oil rig. Most students remember that one and have a pretty easy time knowing what each letter stands for. Now, I'm going to go ahead and tell you guys this. When the College Board redesigned the curriculum, they took out any responsibility of you guys knowing what agents are. So I'm going to make a little note over here. If you come across any question asking you what the oxidizing or reducing agents are, ignore them. Okay? You're going to find those questions all over the place. They're probably still in homeworks that I assign, problems within the textbook. If you look up anything about this on the internet, you're going to find information about oxidizing and reducing agents. And it's fine. It's totally valid, but you're not going to be tested on any of those. So just make sure if any part of a question says, hey, identify the agents, just ignore that part. You don't need to really worry about it for the exams. Okay, now that we have a good list of what these terms you want to definitely be familiar with and which ones to ignore, let's take a look at how they're applied in a chemical reaction. Now, to understand where the electrons are going in a chemical reaction, you need to know your oxidation. Nope, scratch that. I wanted that. Know your rules for oxidation numbers. This you're going to probably have to spend a little bit of time making sure you're very comfortable with. You can find those rules for oxidation numbers in table 4.4 on page, in our textbook it's on page 170. You can also, look up oxidation rules in any sort of electronic device. I'm sure you'll find ones that are exactly the same, maybe just phrased or worded differently. If you want to pause really quick and maybe grab a book, go to table 4.4 on page 170, not a bad idea, or look up right now, be looking at the rules for oxidation numbers. So there's good news and bad news. Most of those rules for oxidation numbers you actually know. I'm not going to list them here. But oxidation number really is has a kind of a simple definition to it. And the oxidation numbers are the charge. Oh, my writing is kind of bad. I'm using a different stylus. Ooh, that made it worse. That's the word the. You know what? Nope, I'm going to fix it. Let's erase that E. I can do better. There we go. Well, you get the idea. The charge an atom or ion appears to have. So this is a way that chemists devise to keep track of what charge something has and where the electrons are going and where they're coming from within a chemical reaction. So when I say that you already know some of these rules, I mean you guys learned them before. You probably know that, hey, if I told you what's the oxidation number for sodium, you would look at sodium on the periodic table, see it's in the first column in the first family, and then say it has a charge of +1, and you'd be absolutely correct. That's its oxidation number. So rules like that you're already familiar with. There's a few rules in that list that are going to be new, and then the really challenging part, though, is actually, the bad news is, the oxidation rules kind of change what you thought you knew. For example, take a halogen, such as chlorine. If I asked you what's the charge of chlorine, again, you probably look at your periodic table, see it's in the halogen family, it's 1 away from its nearest noble gas, it's in the main group 7 family number, and you'd say, oh, it has a charge of -1. And most of the time you'd be right. But chlorine can actually have an oxidation number that can vary quite a bit. From -1, -2, -5, +4, +3, +7, although that's pretty crazy. It can have all sorts of crazy oxidation numbers. Bottom line, you kind of have to keep your mind open to what you thought you knew, and using those rules, figure out what the number is. So definitely take a moment, look over those rules, because now I'm going to kind of apply them in a balanced chemical reaction, and we're going to take a look at how this applies. Let's take a look at a reaction that I showed you guys at very near to the beginning of the year. Let's look at magnesium reacting with oxygen gas to produce magnesium oxide. Make sure this is balanced. There we go. And this is the net ionic reaction for this process, so it's a relatively simple one. But let's go ahead and use those oxidation number rules to assign oxidation numbers to every element within this balanced reaction. So let's take magnesium for example. According to our rules, magnesium is a metal by itself. Nothing else, it's not bonded to anything else, and you see it doesn't have a charge up here. So its oxidation number is going to be 0. Has an oxidation number of 0. Now let's take a look at oxygen gas. Oxygen gas is a diatomic element. Okay, so here it is showing up as O2. This would be oxygen in its elemental state. So because it is in its elemental state, not bonded to anything else other than itself, this would also have an oxidation number of 0. Now let's take a look over here at our compound, magnesium oxide. Magnesium is now bonded to oxygen. To form that bond, it had to take on a positive charge. So magnesium took on its typical charge that we would expect. Positive 2 is its oxidation number. And oxygen here, in order for it to bond, takes on its typical charge of negative 2. And those would be those oxidation numbers. Now, we would identify this as a redox reaction because we see magnesium has an oxidation number of 0, and now it has an oxidation number of positive 2. So its oxidation number changed. Something happened to it as it went from 0 to positive 2. Likewise, oxygen started at 0, and it changed to a negative 2. As long as an oxidation number changes, it should be classified as a redox reaction. Now let's take a look at what happened to each one. Magnesium, as it changed... Oh, I didn't want red. I thought I changed it to black. There we go. As magnesium changed... Oh, that was a really straight line I did. Okay. Magnesium went from 0 to positive 2. Now, think about it. In order to have a charge go from 0 to positive 2, ask yourself, did it lose or gain electrons? Now, hopefully you said it lost. To go from 0 to positive 2 means it lost electrons. Technically, it lost 2 of them. Okay? And since it lost electrons, that fits our definition for oxidation. Magnesium was oxidized. So we say it underwent oxidation. And process of elimination would tell us O2, I'm just going to go right through it. O2 goes from 0 to negative 2. So in order to go from a charge, an oxidation number of 0 to negative 2, oxygen gained electrons. It gained 2 of them. And gaining electrons fits our definition for reduction. So we say magnesium was oxidized and oxygen was reduced. Okay, and we now clearly have identified this as a redox reaction. Little note here, oxidation can't occur, oh boy, can't occur without reduction. Okay, so a very important point. It's a simple one, but it's important that you cannot just, if you're looking at a reaction and all you do is find something that was oxidized, that's impossible. You can't have something only be oxidized and not have a corresponding reduction, and vice versa. You can't have reduction without oxidation. If something is going to lose the electrons, something else has to gain them, right? That's the whole sort of conservation of mass type of idea, right? You can't just have electrons disappear or appear out of nowhere. They have to come from someplace. So kind of let that be a lesson, that if you're looking at a reaction and all you can do is find something oxidized, like clearly you're missing something. You either can't find the reduction or you're misidentifying something that was that oxidized. Maybe it wasn't oxidized. So always kind of keep that in mind. And you can have you can have the same element be oxidized and reduced. That's possible. I'll see if I can find an example of that one. I know they exist in your homework that I give you guys. But take, for example, this is O2, right? That's technically 2 atoms of oxygen. It's possible that one of those atoms could lose electrons and the other atom could gain them. So, like I said, I'll get an example here in a little bit. But, you might have one O go in one compound and another O show up in another compound, right? Oxygen gets around to everything. So if you find it gains electrons in one case and loses them in another, that's totally possible. So as long as you identify, this is an oxidation process and this is the reduction process, you're good. You've identified it's a redox reaction and you found both parts to it. Let's see. Let's look at another example here. Go to a new page. All right, now let's take a look. Let's take a look at this reaction here. Oh, that's my arrow. Here we go. H2SO4. We got some sulfuric acid, and we're going to react it with sodium hydroxide. Strong acid, strong base. Hopefully you're screaming at me. We're going to form a salt, Na2SO4, and water. Okay. Now let's get some practice. Let's assign oxidation numbers to everything in this reaction. This is going to be a good one. I probably should have written that a little bit lower, but that's okay. I'll cram my oxidation numbers. You know what? I'm going to write them underneath. I don't have enough space at the top. Oops. Okay, so here we go. Hydrogen is in a compound, so it's going to have an oxidation number of +1. Oxygen is in a compound. It has an oxidation number of -2. Now here's where some simple math comes into play. Let's see if you guys can follow along here. Sulfur. Okay. Now again, sulfur, you might look at the periodic table and think, oh, it has an oxidation number of -2. Well, false. In this example, in this compound, it can't possibly have an oxidation number of -2. We know, based on our rules, that the overall charge of this entire compound has to be 0, right? There's no charge up here for this whole thing. So everything has to add up to neutral. So let's do a little bit of math here. Follow along. If I have 4 oxygens, right, 4 of them, and each oxygen is -2, each O is -2, and 4 of them, that gives me an overall charge of -8. Bounce over here, 2 hydrogens, each with an oxidation number +1, that's like an overall charge of +2. +2 plus -8 gives me a -6. And I know sulfur is the only thing left, and it has to cancel out that -6 to have an overall charge of neutral, of nothing. So sulfur must have an oxidation number of +6. If you do the math and add all of this up, take each oxidation number, multiply it by how many of that atom you have, the subscript, and then add it all together, you should get the overall charge for the compound or ion. In this case, the overall charge should be 0. +1 times 2 plus +6 times 1 plus -2 times 4 equals 0. Hopefully that wasn't too tricky. I'll kind of go over that again in an organized way, kind of a tool that might help some of you, and then others you'll follow that just fine. It is simple algebra. That's just simple arithmetic. But yeah, I find a lot of students always forget how to do these little numbers here. They make mistakes. Okay, bounce over here to sodium hydroxide. Sodium is in a compound. Okay, it's a metal, but it's bonded, so it's going to have an oxidation number of +1. Oxygen is going to have its bonded -2 charge, and hydrogen will have its bonded +1 charge. Hey, and what do you know? Add all that up, you get the overall compound charge of 0. All right, flow over here to the other side. Sodium is sitting here, bonded in a compound. It has an oxidation number of +1. Oxygen here, bonded in a compound, has its oxidation number of -2. And here we are facing the same issue with sulfur again. Let's do the math. -2 times 4 is -8. Plus +1 times 2. That's +2 added to the -8 gives me -6. So sulfur must have an oxidation number of +6. And keep right on going. Over here, hydrogen is bonded. It has an oxidation number of +1. And oxygen bonded has an oxidation number of -2. Okay, if I did that too fast with the oxidation numbers, pause and just take a moment, look at your rules, make sure you are able to figure out why each thing has an oxidation number of what it is. Make sure it fits those rules and you can understand them. Now, let's take a look here. We see hydrogen, +1, +1, also +1, nothing changed. Oxygen, -2, -2, -2, -2, nothing changed. Sulfur, +6. And +6, nothing. Oh, and nothing changed there. And sodium, +1, +1. No oxidation number change. So hopefully you figured out and determined this reaction is not redox. This is not a redox reaction. We scanned every oxidation number. We found that none of them changed. Therefore, there was no transfer of electrons anywhere in here. And this strong acid, strong base neutralization reaction turns out is not an example of a redox. Pro tip for you guys, pro tip, here we go, take a look. You'll notice if you see a polyatomic ion and it doesn't change from one side of the reaction to the other, you know its oxidation numbers aren't changing. So SO4 remains SO4. Okay? If I took the time to figure out sulfur here, it's the exact same over here. Same thing with the oxygens. They don't change. Okay? So again, just kind of scanning and maybe get better at these things as you look at more and more of them. If you spot a polyatomic, this whole thing looks like a nightmare to try to figure out, but break it down into reasonable pieces. Hey, SO4 remains SO4. I know nothing's happening to it. So it can kind of cut down on the amount of work you have to do in figuring out oxidation numbers, things like that. Okay, now back to oxidation numbers, my little tip. This might help some of you when trying to figure them out and keep track of the math. So this is like a little table that I kind of created to organize the numbers and everything. Take, for example, let's look at carbonate. Oh, that's my arrow again, darn it. Let's look at carbonate. CO. Oh, here, we'll do that in a second. Let me title this up really quick. Help with oxidation numbers. Okay. If you feel you're good with oxidation numbers, then you probably won't need this at all. Feel free to move on. But if you want to take a look, let's look at an example, carbonate, CO3 with a -2 charge. If our job is to figure out the oxidation number for everything involved, what I've done in the past is I create a table, a little grid. I take each element that I'm going to be trying to figure out. Okay, I break it down into three rows. Okay, the first row is oh boy, I should have left more space. The number of atoms. How many atoms do you have of each? Oh, darn it. I didn't mean to write it there. That's under carbon. Here we go. I swear, I know this table. Number of atoms. Okay. Number of atoms. Middle row is going to be the oxidation number. And the last one is going to be total. So the number of atoms we can fill in very quickly. We have 1 carbon and 3 oxygens. So let's go ahead and fill that in. 1 carbon, 3 oxygens. Okay. I do know that my overall charge, all oxidation numbers all added up, have to be -2 overall. So I can fill that in. I fill it in down over here, -2 overall. And now we fill in the element that we know more information on. In that case, it's oxygen. Oxygen, when it's bonded in a molecule, is going to have an oxidation number of -2. Doing the math, 3 times -2 gives me an overall charge of -6. Now, doing the math, -2 has to be the total charge altogether. I already have -6 here, which means this total has to be +4. So +4 plus -6 gives me -2. And now the last piece of the puzzle trying to fill in is what's carbon's oxidation number? Well, if there's only one carbon and it has to have a total of +4, then its oxidation number must be +4. And I've now figured out the oxidation numbers for everything involved, carbons and oxygens. Okay. Again, this might be redundant for you. It might be like, oh my gosh, I can do this math. I don't need a table. Fine. This is not anything you ever have to show for any purpose. It's not a part of showing work at all. But I have found that this does help a couple of students, so I always show it. I try to come up with some way to kind of keep track of everything. That's all. We could do let's come up with another example. I'm going to flip on to another page. Let's look at, oh boy, gosh, the arrow again. Let's look at KClO3, potassium chlorate. So let's create our table. If I want to know the oxidation numbers for everything involved, we've got potassium, we've got chlorine, we've got oxygen. And one more. There we go. And let's do number of atoms, ox number, total. And let's just kind of start filling in the pieces that we know. We have 1 potassium, we have 1 chlorine, and we have 3 oxygens. I know overall this entire molecule has a grand total of a charge of 0. Of all of these, I know oxygen's oxidation number is -2, therefore has a total of -6. I know potassium, being a metal bonded, has a charge of +1, giving us a grand total of +1. Based on these numbers down here, I know that the total that chlorine must provide is +1. The total it must provide is +5, because +1 plus +5 plus -6 gives you 0. And if I only have 1 chlorine, and its total charge has to be +5, then its oxidation number must therefore be +5. And I've now figured out all my oxidation numbers. Okay, what you guys will find with oxidation numbers, there are only certain elements that can really vary when it comes to their numbers. Right, oxygen is almost always -2. There is an exception. I believe it's in your table for oxidation rules. Yeah, it's there. It's only when it's in a peroxide, like hydrogen peroxide, then oxygen has an oxidation number of -1. But other than that, it's -2 all the time. Alkaline metal in a compound, +1 all day. It's elements like chlorine that can have all sorts of varying numbers. So just kind of be on the lookout for that. Usually the larger the atoms get, the greater variance you get in their oxidation numbers, things like that. Okay. Let's look at one more example here. Let's do another reaction. Let's look at lead oxide plus carbon monoxide turns into lead and carbon dioxide. So let's take a look and assign our oxidation numbers for each of our elements involved. Here, oxygen has an oxidation number of -2. It's bonded. Therefore, lead must have an oxidation number of +2. Bounce over here. Carbon monoxide, O again bonded, has a charge of oxidation number of -2. So carbon must have an oxidation number of +2. Here now, lead is by itself. It's a metal. Oxidation number of 0. And further down the line, CO2, oxygen still -2, but there's 2 of them for a total charge of -4. Carbon must have an oxidation number of +4. So we look here, we definitely know we have a redox reaction because we see lead changes from +2 to 0. Okay, so lead ask yourself, did it lose or gain? In this case, lead has gained electrons. In fact, it gained 2 of them. That fits our definition for reduction. Lead is reduced. We see that oxygen's oxidation numbers have not changed at all. So nothing going on there. But carbon, we see, has gone from +2 to +4. It lost 2 more electrons and fits our definition for oxidation. Carbon, we say, is oxidized. Okay, that's really a good intro to redox chemistry mentioned in this chapter. Like I've said before, we're going to go through an entire chapter of this stuff all the way at the end of the year. But this is a good sort of background on this kind of reaction, and knowing oxidation numbers is very, very important. If you guys flip through the rest of the sections in the chapter, the section after this really is just more redox. It goes into really specific reactions. So if you want more examples, I'd say definitely look in section 4.6. Some good pictures and diagrams, things like that. But lots and lots of examples of showing you oxidation numbers and classifying all those types of reactions. And the very last section in chapter 4.7, I wouldn't recommend looking at it. It's super small. It talks about equilibrium. I see no reason to dive into equilibrium at this point. Save that for second semester when we get into it more than you ever want to know. If you feel like reading a paragraph or 2 on equilibrium, knock yourself out. But no need to do that in preparation for the exam on chapter 4. Okay, make sure you guys write any questions you have down, practice this, have your oxidation numbers, have them handy, take a picture of them. Definitely memorize those as best you can. And I'll see you next time.